Hello everyone. Today I managed a board. Okay, let's start in board now. It will be a little bit easier for you. Okay, that's why I managed. See, today's first topic is the characteristics of zero order reaction. Now, what are the characteristics? See, first characteristics. First one is the rate constant for zero order reaction is depend on concentration of what? Reactant. Concentration of reactant. And its unit is mole per liter per second. Okay. Second characteristics of zero reaction is the T half. T half, if you say that in equation of T half, it will be concentration of R naught divided by 2 into K. K is the constant. This is the concentration of the reactant at time 0. That means R naught. That's why you can say T half also proportional to R naught. That means that is T half also proportional to concentration of R naught. Third topic. Third characteristics is the equation. Simple equation. If you write the equation now for zero order reaction, if you write the equation, it will concentration of R naught minus concentration of R divided by T. Now, if you transform this equation in the form of y equal to mx plus c, as we know, the equation of a straight line is y equal to mx plus c. This y is the y-axis. This x is the x-axis. This m is the slope and c is the intercept. Okay, you have to know the concept of equation of the straight line. Now, if we transform this equation in y equal to mx plus c, then what happens? See, if we transform this equation, then it becomes, if we transform this equation, then obviously it becomes R naught minus R equal to KT. Then it becomes what? Concentration of R equal to what? Concentration of R equal to minus KT plus this one R naught. Now, if we compare this one y equal to mx plus c with this equation, if we compare, therefore this one equal to y, this one equal to m, this one equal to x, and this one equal to c. That means m is equal to minus k, x is the t, and c intercept is the R naught. Okay, R naught. Okay. Now, if you see the straight line, okay, now see the straight line. Straight line is this one y mx plus c. This one y axis, this one x axis, x is t. That's why here is t. This one y axis, that means concentration of R. It becomes minus k, no? That means slope is minor. That means slope is decreasing this way. Slope is decreasing this way. This one is the slope equal to minus k, and this much is the intercept. That's why this point is what? Concentration of R naught. Okay, understood now? Okay. Our next topic is the effect of temperature on reaction. Let's see how. Next topic is the effect of temperature on reaction rate. That means how temperature affects the reaction rate. Okay. Now see, temperature is directly proportional with K. That means reaction rate. Wait, not K. Reaction rate is R. This is the temperature. R is the rate of reaction. Okay. That means we can say temperature is directly proportional with reaction rate. If the temperature increases, then obviously R also increases. If the temperature decreases, that means T, obviously R should be decreased. That's why it is directly proportional. Okay. Now see, experimentally it is found that for a chemical reaction, okay, if we increase temperature by 10 degrees centigrade, okay, then it is found that it is experimentally based. Okay, experimental based, it is found that 10 degree increase in temperature increases, then the reaction rate becomes what? Becomes double. That means reaction is 2 times faster than the previous one if we increase 10 degrees of temperature. Okay. Our next topic is the Arrhenious equation. Arrhenious equation. Now, what is the Arrhenious equation? Okay, Arrhenious gives a equations which is as follows: K equal to A e to the power minus EA divided by RT. Okay. Now K is the rate constant. Now what is the terms? Okay, where K is the rate constant, A is known as pre-exponential factor. Remember, this one also constant. Pre-exponential constant. Pre-exponential constant. And EA is the activation energy. Activation energy. Now, what is the meaning of activation energy? Remember, activation energy means the energy which is required to activate the reaction to form product. Okay. Now we will discuss, okay, what is the graphical representations or what is the actual meaning of activation energy. Okay. Now see, next is the R and T. R is the obviously gas constant and T is the temperature. Okay. See. Now let us take an example of reaction. Okay. To understand in better way, let us take an example of reaction. See. Suppose I'm taking an example of, suppose I2 iodine molecule reacts with H2 and produce 2 molecules of HI. This is an I2 molecule, H2 and HI, hydrogen iodide. Now, if we look the mechanism of the reaction, that means how the reactions perform or what are the steps involved in the reactions. See the mechanism. Okay. Mechanism. The mechanism is as follows. This one hydrogen, this one also hydrogen. Okay. Next, iodine and also iodine. When it react, this one is reactant. Okay. Next thing is the bond between this hydrogen and iodine partially, okay, disappears and form a new bond which is also partial, not fully. In this step, suppose I am taking this way. this dotted bond is the partial bond. Hydrogen is partially bonding with iodine and also its own hydrogen atom. That means these bonds are not completed bond, not completely stable bond, or you can say there is no bond. You can't say, okay? There is a bond. That means there is an interaction. Now see, this is the intermediate step, okay? And this type of molecule or this type of complex is known as activation complex. Activation complex. And simply it is known as intermediate. In this form in intermediate position between the reactant and product. Now we are writing the product. Second thing is the this bond, the bond between hydrogen and iodine partially or completely broken and form Hi plus another Hi. This one reactant, sorry, this one product. Here bonding between hydrogen and iodine. Here bonding between all the hydrogen and iodine, which is not a full bond, okay, which is known as activated complex and intermediate. In the last step, when the products form, it becomes Hi. That means this bond is broken and this bond formed. Hi. That means that's why here is two molecule of Hi. Now, if we see this reaction graphically, okay, graphically, see. And the important point of the Arrhenious equation. Okay. Now, the intermediate, that means this one. Okay, intermediate means this one, this complete intermediate is highly unstable, okay, and highly unstable and rapidly transformed into product, okay. And the thing, it exists for a very short time period, okay. This is the main topic or main concept between the intermediate, okay. Since it is highly unstable, no, that means it has high energy because it is unstable, okay. Now let us draw the energy profile diagram of the Arrhenious equations. Now, okay, please manage, okay. My board is little bit small, okay, that's why. If we just want to draw the energy profile diagram of reaction, okay, here is reaction coordinate. It means how the reaction is performing step by step, okay. This one is the energy. If you say in book, it is written as potential energy. Potential energy means simple energy, okay. Now if you write the reaction, here is the reactant means H2 plus I2. Then obviously it forms intermediate, which is unstable and in very high energy. It have very high energy. Now if we add this one is the intermediate and product is little bit lower. This one is the intermediate, and intermediate is this one. See, this one is very high energy, no? If we take this one, very high energy, but is smaller, lower energy. But if we look clearly, the product, which is Hi, okay, two molecules of Hi, it have lower energy than the reactant, because this reactant, sorry, this product molecule have lower energy because it is little bit more stable than the reactant as well as the intermediate. That's why it is in lower energy, but reactant is little bit higher energy, and the intermediate which is in very high energy. Due to this high amount of energy of intermediate, it is highly unstable and exists for a very short time. Okay. Next, energy difference between this intermediate, or you can say activation complex, and the reactant is known as what? Activation energy. Why? Okay. Suppose we have taken this amount of energy, the reactant molecule is stable. Then the reaction is proceeding, or reaction is going on, then the energy becomes a little bit higher. It goes off in this intermediate states, having the energy this much. Okay. Simple thing, in other word, okay, this energy is needed to activate the molecule. Isn't it? This much of energy is needed or is supplied to activate the molecule into the intermediate state. From this intermediate state, the molecules, in the molecules, some chemical bonds is making and some chemical bonds forming, so that it produces product. And the product molecule is very stable. That's why it occurs in the lower energy. The energy of the product is also lower from the reactant. That's why it is more stable. This one is stable, this one is highly unstable, this one is more stable. Okay. The help of this Arrhenious equation, we can find the activation energy of a reaction. Now, in two steps we can find out, okay, activation energy. Now, first step, or you can say first method. First method is the graphical method. With the help of graph, we can find out the activation energy. Okay. Now, see. First one is the graphical method for the determination of E. Okay, activation energy. How we can find out the activation energy with the help of graphical method. Okay. See, as we know, wait. As we know, K equal to A e to the power minus EA by RT. Isn't it? If we take ln in both sides, okay, see, ln K equal to ln obviously EA by RT, no? This ln means simply one form of log, okay? But in chemistry, first of all, we have to take ln. We can't take directly log. Okay? ln K. If you see, here's the multiplication, no? That means ln A plus what? ln E to the power minus EA by RT. As we know the formula, ln AB, as we know formula, ln A into B is the ln A plus ln K, ln B. Same formula as the log. Log A into B equal to log A plus log B. That's why here is ln AB equal to ln A plus ln B. Okay. See the next step. Now, another formula is that ln, okay, ln e to the power x. Ln e to the power x equal to x ln e. And ln e is the value of 1. That means x. This formula we have to apply here. How? See. The second step, next step, ln k equal to ln a, no, plus this one ln e to the power x. This one suppose taken as x. Then x ln e minus x into ln e. As you know, ln e equal to 1. That means it becomes 1, no? Here, that's right. Since ln E equal to 1. Now, then this equation becomes ln K equal to ln A minus EA by RT. Okay. Now you have to transfer this ln into log. How? When we transfer ln into log, we have to multiply it by a value 2.303. 2.303, then it becomes log K equal to 2.303 log of A minus EA by RT. No, simple thing. Okay. Now, if we want to this cancel the 2.303 both sides, then we have to divide both sides with the help of 2.303. Then it becomes log of K equal to log of A minus, sorry, this one EA divided by 2.303 RT. Now, if we see clearly, this one becomes what? Y. Okay, this one, let me write in different arrangement. Okay, wait, let me write in different arrangement. This one, log of K equal to minus EA by 2.30303 RT log of A plus log of A. Then if you just compare with the mx plus c, which is the equation of straight line, then it becomes y. This one t is here. Okay, this one m means this, x means t, and this one c. Y-axis is the slope, t is the in x-axis. Remember, 1 by t, not simple t. Okay, this one log of A. Log of A is the c. Now, if we just draw this y equal to mx plus c equation in the graph, then we get this way. Okay, then we get the graph this way. Y-axis no, that's why log of K. X-axis 1 by t. C in the intercept, suppose here in this point, log of A. Slope is negative, that's why the curve should be decreased. The slope is EA, that means accretion energy by 2.303 R. If we add this one, slope equal to minus EA by 2.303 R. Remember, this slope, if you want to evaluate the slope with the help of run, then we have to know about the graphical representations, how we calculate the slope. Suppose it is given that this height, okay, this height and this base. If we take this one as a right angle, obviously it becomes base of right angle. This become perpendicular and this become hypotenuse. Then this angle, that means tan theta, that means this one angle, tan theta is the slope. Tan theta is the slope, is equal to what? P by B. P by B. P is the this height and B is this length. Okay, tan theta, that means slope equal to P by B. If we want to evaluate EA with the help of slope, then we have to know the graphical representations, how we calculate the slope. That was slope equal to, for this triangle, that is right angle, P by B. This P by B equal to this minus EA by 2.303. Okay, understood? No? Okay. Next is the determination of activation energy for a reaction with the help of what? Theoretical method. Okay, theoretical method. This one, now it is theoretical. 2. theoretical method for the determination of activation energy. How it is? See, let K1 and K2 are the two rate constant for a reaction at time T1 and T2. Okay, T1 T2. Then the activation energy or not activation, sorry, the Arrhenious equation we can write log of K1 equal to log of A minus what? EA by 2.303 RT1. Similarly, for K2 in time T2 is the log of A. Remember this one, A is the pre-exponential factor, which is a constant. That's why it is not changed in either temperature. This one EA equal to 2.303 RT2. Suppose it is taken as 1, it is taken as 2. Now if we subtract 2 from 1, 2 minus 1, now 2 minus 1 becomes log K2 minus K1, log K2 minus log of K1, and this one cancel, no, and it becomes minus EA by 2.303 RT1 minus plus 2.303 RT. Okay. Now again log A minus log B formula, log of A by P, and second thing is that if it does interchange, then it becomes EA by 2.303 RT. This one, sorry, this one is 2, this one 1. Then it becomes 1 minus EA by 2.303 RT2. Then it becomes, if we take LCM, no, wait, if we take common from this, wait, if we take common EA by 2.303 R, then it becomes EA by 2.303 R, then it obviously 1 by T1 minus, sorry, 1 by T2. Okay, 1 by T1 I'm writing out. Okay, writing one out. Here it is log of K2 by K1 equal to EA by 2.303 R, and becomes the LCM of T1 and T2, T1 T2, and this one becomes T2 minus T1. Okay, therefore okay, this one is the main equation. This one is the main equation to determine the activation energy for a reaction in theoretical method. Okay, next topic is the effect of catalyst on a reaction rate. Okay, what is the effect of catalyst on reaction rate? First of all, note to this concept, we have to know what is catalyst. See, effect of catalyst on reaction rate. Effect of catalyst on reaction rate. Okay, now see, first I have written some point wise. Okay, some point wise, so that you will understood very easily. Okay, a catalyst is a substance. It may be liquid or it may be soluble. Okay, substance which increases the rate of reaction. Rate of reaction. Without, but remember this one, catalyst increases the rate of reactions, but itself does not involve in the reactions. But without itself undergoing any permanent chemical change. Now, what is the meaning of this sentence? Okay, a catalyst is a substance which increases the rate of reactions, but itself it does not undergo any permanent change. Permanent change means it can take part in some chemical reactions. Okay, but in the final step or in the middle step, it is removed as the same catalyst of the previous form. Okay, that's why I'm saying it does not undergo permanent chemical change. Okay, that means the catalyst remain as it is throughout the reaction. Next, catalyst provides a alternate path for the reaction by decreasing the activation energy. Okay, the main concept of catalyst is the decrease in activation energy. The catalyst decreases the activation energy. If the catalyst decreases the activation energy, or you can say if for a reaction the activation energy for the particular reaction is decreases, that means the reaction takes little bit short time. You can say faster reactions, lower the temperature. Okay, now see, graphical dimension, it will clear. See this one, energy profile, sorry, reaction. Here is reaction coordinate, here is energy for the reactions. Now if we write a reaction without catalyst, okay, simple reaction, here is the reactant, this one intermediate, or you can say activation complex, this one is the product, this one without catalyst, or you can say in absence of catalyst the reactions proceeds via this way. Now if we add some amount of catalyst in the reactions, then what happens? What is the change in this energy profile diagram? The energy of the reactants as it is. Okay, the energy of the reactants does not change, but the energy of the activation complex or intermediate little bit decreases. Okay, now see. Remember this one. The activation energy of this reaction is this one, no? As I explained earlier. Okay, this one is the activation energy. Maybe I forgot. Okay, activation energy is the energy difference between the intermediate and the reactant molecule. This one is the activation energy. This one, activation energy without catalyst. Wait, let me write in blue ink. Okay, it will be better in blue ink. Okay, this one is the activation energy. This one is the activation energy. Now if we add little amount of catalyst to the reaction, then what will happen? then the reaction proceed via this way. Remember, the energy of the reactant as well as the product remains same, but the energy of the activation complex or intermediate decreases. This one is the new activation energy with catalyst. This one is the activation energy with catalyst. Here you can clearly see, as we added the catalyst, the activation energy decreases, which increases the reaction rate. Okay.